Sample spaces and probability. Sample space and classical probability. Suppose a family has 3 children. What are the possible birth outcomes for the 3 children with regard to gender? There could be 3 boys. There could be 2 boys and a girl, where the girl is the youngest, the middle child, or the oldest. There could be 1 boy and 2 girls, where the boy is the oldest, the middle child, or the youngest. The only other possibility would be that all 3 children are girls. A sample space is the set of all possible outcomes of a probability experiment. This collection of outcomes would be the sample space for the birth outcomes for a family with 3 children. An event is a collection of the outcomes of a probability experiment. Classical probability is defined as the number of outcomes in an event divided by the total number of outcomes in the sample space. This would be expressed with probability notation as the probability that event E would occur equal to the number of outcomes in event E divided by the number of outcomes in the sample space. So let's find the probability that the family with 3 children would have exactly 2 boys. There are 3 total outcomes with 3 boys and 8 outcomes in the sample space. So that probability would be 3 out of 8. The probability that the family would have 3 girls will be calculated by finding the number of outcomes with 3 girls, which is 1, and dividing that by the size of the sample space, which is 8. So the probability could be equal to 1 out of 8, or 1/8. Empirical probability. Empirical probability relies on experience and observation to determine the likelihood of outcomes. Given a frequency distribution, the probability of an event being in a given class is expressed as the probability that an event E will occur is equal to the frequency for the class divided by the total frequencies in the distribution. This is abbreviated as the probability that event E will occur is equal to F divided by N. The table below is an example of a political party affiliation poll. The participants responded either Republican, Democrat, or Independent with the given frequencies. From this table, a researcher will determine that the probability that a Republican was selected from this population is equal to 45 out of 100. This table gives us the number of U.S. Social Security recipients by age for the year of 2014. The number of beneficiaries is given in thousands. The probability that a randomly selected U.S. Social Security recipient would be between the ages of 15 and 54 would be expressed in probability notation as the probability that a randomly selected individual would be between 15 and 54. From the table, we see that this probability would be 5,209 divided by 48,371. Now, suppose that we were asked to find the probability that a randomly selected U.S. Social Security recipient is older than 54. We can also express this as the probability that a randomly selected recipient is 55 years or older. This would be a convenient way to express this probability since this is the way the table is organized. The probability that a randomly selected recipient is 55 or older can be determined using the complement by subtracting the probability that a recipient is between the ages of 15 and 54 from 1. So, to find this probability, we would evaluate the expression 1 minus 5,209 divided by 48,371. This result would be 43,162 divided by 48,371. Let's go ahead and follow along with your student notes. Objective 1. Determine sample spaces and find the probability of an event using classical probability or empirical probability. Probability is the chance that an event occurs. Probability is the basis of what we learned before as inferential statistics. Here are some basic concepts. Processes such as flipping a coin or rolling a die are called probability experiments. A probability experiment is a chance process that leads to well-defined results called outcomes. An outcome is a result of a single trial of a probability experiment. A trial means flipping a coin once, or rolling one die once. Answering a multiple choice question with 4 options by a single random selection. When tossing a coin, there are 2 outcomes, head or tail. A multiple choice question with 4 options or outcomes, A, B, C, or D. A sample space is the set of all possible outcomes of a probability experiment. Here are some examples of experiments and their sample spaces. For example, when you toss one coin, the result is either head or tail. When you roll a die, a 6-sided die in particular, the options are 1, 2, 3, 4, 5, or 6. To answer a true or false question, 2 options of true or false. But you also have other types of experiments, including tossing 2 coins. When you toss 2 coins, you can get both heads, you can get both tails, you can get the first coin is head, the second coin is tail, and you also can get the first coin tail, the second coin head. These sample spaces have been found by observation and reasoning. Charts and tree diagrams help organize the possible outcomes. Here's an example of a sample space for rolling 2 die. Let's find the sample space for rolling 2 standard 6-sided dice. Each die can land in 6 different ways, 1 through 6. And here we are rolling 2 dice. The sample space can be shown in what's called an array. So if we roll a 1 in die number 1, but also roll a 1 in die number 2, the result is 1, 1. If we roll a 1 for the first die, but a 2 in the second die, the result is 1, 2. And on it goes in the same pattern. If the first die is 1 and the second die is 3, 1, 3. If the first die is 1 and the second die is 4, 1, 4. And randomly, if the first die, let's say, was a 5, and the second die was rolled as a 3, that would give us 5, 3. Filling out the rest of this table gives us the following 36 outcomes. And this would be known as our sample space. The sample space being all the elements or possible outcomes of this situation. Once again, there are 36 different elements in the sample space. Using the chart, we could be sure that we listed each pair without repeating or leaving any out. In other words, we have every possible outcome for this particular probability experiment listed in this array. Another method to find all possible outcomes of a probability experiment is to use a tree diagram. For example, in a family of 3 children, find the sample space for the birth order by gender of the children. To do so, each time a child is born, there are two gender possibilities. We draw two branches for the firstborn child. We do the same for the secondborn child for each of the firstborn options. And then we repeat for the third child. As you can see, the first child is based off these first two branches, either boy or girl. And from each subsequent child, we branch off twice more. Now let's imagine the first child is a boy, the second child is a boy, and the third child is also a boy. That outcome will be known as BBB. Or what if we had the scenario where the first child was a boy, the second child was a boy, and the third child is a girl? That outcome will be known as BBG. Filling out the rest of this tree diagram gives us the following outcomes. The results for each possibility is a combination of three outcomes. An event consists of a set of outcomes of a probability experiment. An event can be one outcome or more than one outcome. An event with exactly one outcome is called a simple event. An event with more than one outcome is called a compound event. Three interpretations of probability. Classical probability. Classical probability uses sample spaces to determine the numerical probability that an event will happen. Classical probability assumes that all outcomes in the sample space are equally likely to occur. If a sample space has n equally likely outcomes, and an event has k outcomes, then the classical probability of event A is as follows. That is the number of outcomes in A divided by the number of outcomes in the sample space. Since we are using n for the sample space and k for the event A, we get the formula k over n. Example, what is the probability that all three of the children are of the same gender? The sample space has 8 outcomes. That is boy, 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 girl, boy, girl, boy, and so on to girl, girl, girl. Since 2 of the outcomes have children of the same gender, that is boy, 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 and girl, 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 we have the following probability. That is to say, 2 outcomes, that is boy, 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 girl, 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 divided by the 8 total possibilities of having 3 children in a family, which reduces to 1/4 in this case. Therefore, the probability that 3 children are of the same gender in a 3-child family is 1/4. Four probability rules. There are 4 characteristics of probabilities. We use them to solve probability problems, for understanding the nature of probability and deciding whether the answers to probability problems are correct. The first rule is very important, and that is to say that the probability of any event is between 0 and 1. And this is a very important rule that we must follow at all times. Here's a diagram to further explain. 0 represents the impossibility of an event. 1 represents the certainty of an event. And you'll notice in the middle, it might be 50-50. To the left would be an unlikely event. To the right would be a likely event. So what would be the probability of rolling a 5? If I'm rolling a 6-sided die, and let's say this is a fair die, and each side is equally likely, then the probability of rolling a 5 in one try is 1 out of 6. But to find the probability of rolling a multiple of 3, we must first consider that there are 2 numbers in a 6-sided die that is a multiple of 3. That is to say, the probability of rolling a multiple of 3 would be 2 out of 6. And the reason why is because 2 values from the die, 3 and 6, are multiples of 3. The second probability rule of the 4 is that the sum of probabilities of all outcomes in a sample space is 1. That is to say, if I add up every single probability of all outcomes in any given sample space, you will get 1. The third rule is that if an event cannot occur, that is, the sample space is empty or the event is impossible, its probability is 0. So the probability of A equals 0 when event A cannot occur. So let's find the probability of rolling an 8 when rolling a standard fair 6-sided die. Pretty obvious that when you roll a 6-sided die, the probability of rolling an 8 in one try will be 0. And this is because it is impossible to have an outcome of 8 when rolling a 6-sided die. Rule number 4. If an event must happen or is certain, then the probability will be 1. So let's go ahead and find a certain probability. Let's find the probability that rolling a value that is less than 7 using a standard 6-sided fair die. Well, clearly there are no values of 7 on a standard 6-sided fair die. Thus, the probability of rolling a number less than 7 is equal to 1. It is certain, because all outcomes when rolling a standard 6-sided fair die are less than 7. Complementary events. The complement of an event A is the set of outcomes in the sample space that are not included in the outcomes of event A. This is denoted by A bar. Find the complement of an event. Let's find the complement of event A, and let's let event A be a day that begins with T, that is Tuesday and Thursday. Therefore, the complement to event A will be a day of the week that does not begin with T. Therefore, A bar or A complement would be Sunday, Monday, Wednesday, Friday, and Saturday. So the complement of event B, which is rolling 2 die and getting an odd numbered sum, which is 3, 5, 7, 9, or 11, would give us the complement of rolling 2 die and getting a sum that is not odd. That is to say, the sum is 2, 4, 6, 8, 10, or 12. So once again, B would be the sums of 3, 5, 7, 9, or 11. B complement or B bar would be the other sums, 2, 4, 6, 8, 10, or 12. If the probability of an event or the probability of its complement is known, then the probability of the other can be found by subtracting the known probability from 1. So for example, if I wanted to know the probability of A bar, all I simply do is take 1 and subtract the probability of the event A occurring. Or I could take the probability of event A to be equal to 1 minus the probability of A complement. And the reason why both these formulas work, and they become very important as we progress in this class, is because if you actually take the probabilities of A and the probability of A bar and add them up, you get 1. All three of these formulas are very important and become increasingly important as we progress in the next few weeks. Empirical probability relies on actual experience or observations to determine the likelihood, relative frequency, of outcomes. Given a frequency distribution, the empirical probability of an event being in a given class is as follows. It is the frequency for the class of interest divided by total frequencies in the distribution. So for example, a survey of the blood type of 50 people revealed that 21 had O blood, 22 had type A blood, 5 had type B blood, and 2 had AB blood. For example, the probability that a person has type O blood would be 2 out of 50, or 0.04. The probability that a person had type A or AB blood, in this case, you take the people that had type A blood, add it to how many people had type AB blood, and here we get 24 out of 50, which reduces to 12 out of 25, or 0.48. Notice here that we added the probabilities based on the word or here. The probability that a person has neither type A nor AB blood, what you do there is you go ahead and you take the previous probability and you subtract it from 1. Notice here that the previous probability was looking for the probability that a person had type A or AB blood, whereas this one is the complement to the second probability. So simply take 1 and subtract 12/25, giving us 0.52. And notice how if I were to add 0.48 and 0.52, we would get 1. Empirical probabilities have the same value as relative frequencies of the outcomes in the distribution, something we have actually some experience with from previous sections. The law of large numbers states that as the number of trials of a random experiment increases, the empirical probability will approach the classical or theoretical probability. Suppose a fair die is tossed. The classical probability for each value from 1 to 6 is 1/6. For an experiment using a fair die, as the number of tosses that result in a 2 increases, the empirical probability of tossing the number 2 will approach the theoretical probability of 1/6. Now, it might take you a long time before you actually roll a 2. In fact, it may even take you well more than 6 rolls to roll an actual 2. But the idea of the law of large numbers is that the more you roll the die, the more likely you'll roll a 2 on a 1 to 6 probability. Now, if a die is tossed many times and the empirical probability for tossing a 2 is not approaching 1/6, then it is likely that the die is not fair, meaning that the die could be weighted The die could actually have the number 2 missing from one of the sides. There could be many possible reasons for why the die is not fair. Subjective probability is based on an educated guess, or an estimate, an opinion, and maybe even inexact information. The probability is based on the person's experience and evaluation of a solution. For instance, a weather forecaster predicts a 65% chance of rain, or a sports writer may say that there is a 70% chance that a particular team will win the pennant that year. These are examples of the use of subjective probability.